Hello, everyone. We are the redshift group, and our project was about taking a sample of galaxies from the Sloan Digital Sky Survey and looking at their redshifts to get a picture of the evolution of galaxies in our universe. My name is Nathan Streater, and my teammates are Charis, William Ostling, and Nidhi Shah, and this is our presentation.
The idea of redshift is that when an object is moving away, it's slightly redshifted on the visible spectrum. The diagram on the bottom left shows the Doppler shift, where when the star is moving away, the light waves are elongated, which moves the light towards the red side of the spectrum, and vice versa to the blue side for objects coming closer. Later scientists made the connection between redshift and the general expansion of the universe. This cosmological expansion differs from the Doppler shift because the objects are not moving away, but rather the space between them is expanding. The raisin bread diagram on the right demonstrates how this expansion works. The bread is a space which is expanding and causing the raisins, the matter within that space, like galaxies, to move away from each other. Specifically, raisins that started out closer together moved smaller distances away from each other compared to those that started out further apart. This holds true for any raisin and means that the further a raisin, the faster it's moving away. Using this rule of cosmological redshift, almost all objects in the universe can be seen to be moving away from us, and the further these objects are, the faster they're moving away. Redshift allows scientists to measure the most distant galaxies, and since light takes time to reach us, this allows scientists to look into the past at the early universe. Understanding these trends is very important in understanding how the universe began and evolved and how it will continue to do so.
So our main goal for this project was to explore whether or not there were any correlations between galaxy redshift and galaxy type by compiling, organizing, and studying a database of over 200 galaxies. We aimed to collect specific measurements and note any possible biases that may have altered our results and data. This would hopefully help to answer questions on topics such as the evolution of galaxies and early universe conditions. In order to achieve these goals and complete our study, we used data and measurements from SDSS, the Sloan Digital Sky Survey, Data Release 6. Each group member classified over 50 galaxies from the plates of the SDSS archives and also noted the galaxy's right ascension, declination, redshift, and the redshift error. Using tools such as visual images and galaxy spectra, we were able to classify these galaxies by their morphology and distinguish whether or not they were considered active or non-active galaxies. From there, we could organize all this data and search for trends or patterns. These are some examples of different types of galaxies and their respective spectrums that we encountered and classified through our research. We also have examples of galaxies that were more challenging to classify due to factors such as high redshift and distance or low image resolution. And finally, we have an example of a unique ring galaxy we were able to find and classify through our research. Displayed here, we have galaxies demonstrating the difference between non-active and active galaxies. An active galaxy is defined to be a galaxy with an active nucleus, containing a black hole gaining mass by feeding on the surrounding material. As this material spirals into the black hole at the nucleus, it reaches high temperatures, exciting the surrounding gas, resulting in emission. So one of the ways we can tell whether or not a galaxy is active is by searching the galaxy's spectra for emission lines. As you can see, the active galaxy's spiral spectra indicate strong H-alpha and oxygen emission lines, while the non-active galaxy's spectra does not, and also contains a few clear absorption lines. These are all factors we would take into account in order to classify each galaxy as active or non-active.
While analyzing the data, we found sources of bias which we worked to eliminate. We found more elliptical and spiral galaxies than interacting and irregular galaxies, giving us less data to work with in those categories. We also found a lot more galaxies at low redshift, simply because those galaxies are larger and brighter, making them easier to spot. We noticed that at higher redshift, there was generally a higher redshift error. This is simply because at a higher redshift, galaxies tend to be much dimmer, so their spectrum is a lot noisier, making it harder to accurately determine their redshift. To combat this bias, we used percentages and composition instead of initial count. We also noticed that the redshift range from 0.2 to 0.3 had a deficit in our original sample, so we added 30 additional galaxies around that range. To create the pop graph, we split redshift into 10 bins, then totaled the amount of galaxies per bin, and created percentages for each galaxy type. We decided to add the percent interactive and irregular galaxies simply because it was hard to tell them apart at such a high redshift. From the graphs below, you can see a third order polynomial fitted line is fitted. And you can see that more irregular and interacting galaxies appear at higher redshift. This is because we see them farther in the past when galaxies were closer, and so they had much more of a chance of interacting. We also see more spiral galaxies at a low redshift, and this is because we see them closer to real time when they have less of a chance of getting disrupted because galaxies are farther apart. This graph details the percent makeup of active galaxies versus redshift. The large amount of active galaxies at a low redshift is contaminated by spiral galaxies, most of which we see have starbursts, and so they appeared to be an active galaxy. The slow rise between 0.1 and 0.4 redshift corresponds to true active galaxies, and the sharp cutoff at around 0.5 is where SDSS cuts off H-alpha lines due to telescopic restrictions.
One of the challenges we had during this project was that classifying the distant galaxies could be difficult, since sometimes they were only pixels across in the image. In addition, some images would unfortunately have artifacts like misaligned plates, which could leave parts of the image as the wrong color or offset and misshapen. Another thing to keep in mind was that there was no magic number or way to tell apart different types of galaxies 100% of the time. Often we were making our best judgments when we were classifying these galaxies. Working over Zoom also brought its own challenges, like a time difference between some of us, and we were also only able to classify around 230 galaxies, which might not have been a large enough sample to remove some of the biases in the data. Our final main challenge was the limitations of the telescope used for the survey, like galaxy spectra being cut off and detecting far more low redshift galaxies than ones that were farther away. However, we did have several big highlights and favorite parts of the internship. We got to see a wide variety of galaxies, from massive nearby grand design spiral galaxies to the interesting ring galaxy and faraway blobs with no real shape. We were also able to use helpful visual tools and spectral images of galaxies to make our classifications easier and more accurate. Also, being able to work with students and mentors that shared an interest in astronomy and research made SEAS just that much more engaging.
So for me, the SEAS internship not only taught me new skills and techniques in areas including astronomy, scientific research, and computer science, but it also reinforced my vision of a future career in astrophysics and space exploration. It helped me to realize the possibilities and encouraged me to explore different aspects of that career path, including striving for a career with NASA and applying to be an astronaut in the future.
My time at SEAS strengthened my passion for observational astronomy. I've always loved astrophotography, and so analyzing real telescopic data that researchers use was really amazing, and spectra analysis was something new and fun to learn. I also learned many new skills, like querying and analyzing survey data and creating graphs in Python meant to remove as much bias as possible.
Being a SEAS intern taught me what exactly an astronomer does and how various skills, many of which I hadn't considered before, can be used practically. And most importantly, I learned about the various skill sets involved in NASA's work and more about the professional career that I might want to pursue.
I really enjoyed the speaker series where I got to learn about the wide variety of research fields in not just astronomy, but Earth and space science as a whole. I also got an in-depth look at astronomical research and new scientific concepts with real galaxy data.
This work was made possible by our amazing project mentors and astronomy group leaders, Dr. Judit, Ries, Olivia, Kuper, and Kerry Johnson. The SEAS Association and NASA made this entire program possible, and the Sloan Digital Sky Survey and the European Space Agency made all their data public, allowing us to survey it.